Hi, welcome back. Hope you're doing well. Uh, we now move on to the next chapter in the notes, which is on orthogonality, which is also chapter 4 in the Strang textbook. Okay, and in Rn, this is before we start talking about anything, in Rn, from a geometric perspective, orthogonal really means perpendicular. Okay, so the picture that you should have in your head of orthogonality is that of perpendicularity, of like perpendicular lines or a plane and its normal vector. But the definitions that we'll make sense in more generality than just Rn. So you can talk about orthogonality in other vector spaces where you don't necessarily have a geometric picture, or maybe even in higher dimensions where it's hard to think of a geometric picture. Okay, it's a really important concept because it gets at some sort of notions of distance and angles, which actually is not really covered in Math 308. If you go back and think about it, you never really talked about it so much. And that's because Math 308 at UW is a 10-week course in linear algebra, and this stuff fits into a standard 15-week course in linear algebra. At the semester schools that I've been at, I've taught it. And so this is kind of really fundamental stuff. It's really more like, it's more mathy stuff. It's less application-y stuff. So if you took linear algebra elsewhere, you've maybe already seen this. But if you took it at UW, some professors actually do cover it because it's pretty fundamental. But I didn't when I taught 308, so this is, I'm assuming that this is new. Okay, so let's recall some definitions. So I'm going to let V be the vector V1 through Vn, W be the vector Wn through Wn. These are both vectors in Rn. Then the dot product is hopefully something you're familiar with. The dot product of V and W is, well, first let me write out the way that you probably first think about it, which is just you multiply the corresponding components and then you add them together, right? And this is a real number. Okay, so one way to think about this is just as this sum, where you multiply corresponding components and you add them all together. But another very useful way to think about this is you can think of this as a multiplication of the transpose of V, that's a row vector, times W, right? Because if you think of this thing is V1, V2, Vn times W1, W2, Wn. And if you were to do the matrix multiplication here, it would yield exactly the dot product. Okay, so this is sort of very nice compact notation for the dot product in terms of a thing we already understand. Okay, once you have the notion of a dot product, the norm of V is defined to be, so the symbol that you use are these sort of a doubled absolute value bars. That's the norm of a vector. And it's defined to be the square root of V dot V, or the square root of V transpose times V. In other words, since you're taking the same vector twice, it's just the square root of the sum of the squares of all the components, which in the notes is also written like this. Okay, so in other words, what we're doing is we're introducing a notion of length into our vector spaces, which isn't really part of Math 308, but is a very useful, important feature of these vector spaces. At least Rn, right? This is the norm. Don't get it confused with the squared norm. So the squared norm of V is just when you don't take the square root. So it's just this. Okay, so if you dot V with itself, you get the squared norm. To get the classic norm, you have to take the square root. Okay, and in Rn, right, if you draw a picture, say in R2, you should check for yourself by using the Pythagorean theorem, the norm is exactly the length. Right, so this is in Rn, this is just equal to the length of the vector, the magnitude of the vector. Okay, also, perhaps you remember from maybe Calc 3 or something, that if you take the dot product of two vectors, first of all, it doesn't matter which order you take the dot product in. And then maybe you remember that it's the length of V times the length of W times the cosine of the angle between them, where theta is the angle between v and w. Okay, in this sense, once we've defined the dot product on a vector space, we also have a notion of angles between vectors, which is also a very useful notion, which, by the way, is not really covered in Math 308. So distance and angles are both really important. There's a geometry to the vector space, and it's sort of a new concept here. Okay, so in particular, in Rn, if v and w are perpendicular, well, then that means that the angle between them is pi over 2. So, and cosine of pi over 2 is 0, so v dot w is 0. So this is the notion that we're going to extend, generalize, and we'll just say, okay, well, if you have a dot product, an inner product on a vector space, you call two vectors orthogonal if their dot product is equal to 0. That's the definition. So for any VW in Rn, and this definition works in other vector spaces as well, we say that V and W are orthogonal if you take the dot product and you get 0. Okay, but it's the same. No matter which order you take the dot product, you get the same result. Okay, and the way that we write this is we write V is perpendicular to W, or V is orthogonal to W. We use this perpendicular symbol. Okay. Again, the picture to keep in mind is literally two vectors that are perpendicular in R2 or R3 or Rn. Okay, and one thing that we have is sort of a Pythagorean theorem, which is if V and W are vectors in Rn, and their dot product is 0, in other words, if they're perpendicular, they're orthogonal, then if you take the length of V squared and you add to the length of W squared, you get either the length of V minus W squared, which is the same thing as the length of V plus W squared. Okay, what do I mean by this? Here's the picture. Let's just draw the picture in R2. So let's take a vector V. Let's take a vector W. And I'm assuming that they're orthogonal, so let's draw them perpendicular to one another. Now we know that by the Pythagorean theorem, the length of the hypotenuse here should be the length of V squared plus the length of W squared. Take the square root, right? So the square of the length of the hypotenuse is the length of V squared plus the length of W squared. But if you consider what is V plus W and what is V minus W, so V minus W is V and then you add negative W. And that's negative W, there's a right angle here. This vector is V minus W, which is definitely the same thing that has the same hypotenuse, right? It's got a side of length V and a side of length W. Maybe I should make W longer. Let me do that to make it more illustrative so it's clear what I'm doing. Let's make W much longer. Then V minus W is you take V and you subtract off W. So it's the vector going in this direction. This vector is V minus W. And you can see that that's the same thing as, well, V plus, that's the same thing as the hypotenuse of this triangle here, right? The picture is the same on both sides. What is V plus W? V plus W is you take V and you add the length of W here. And V plus W would be this vector then, which is also the hypotenuse of a triangle that has V as one side and W as the other side. So these two vectors should have the same length, and the squares of those lengths should be the length of V squared plus the length of W squared. Okay, that's in Rn, but I mentioned that you can do this for even like any what's called an inner product space, but also if I want to talk, I can talk about two subspaces of Rn being perpendicular, right? Because, sorry, this was just for vectors in Rn. I said this vector is perpendicular to this vector. But recall also from Calc 3 that if you have a plane and you have a normal vector, you can think of those two things as being perpendicular to one another. But that's not two vectors. That's a plane and a line, right? Or a plane and a vector. So what do you mean when you say that this normal vector is perpendicular to this plane? What you mean is that it's perpendicular to every single vector in the plane. So we're going to extend this definition to subspaces of Rn. So now I can talk about a whole plane being perpendicular to another whole plane, which can't happen in R3, but can happen in R4. So here's the definition. I created an extra page for no reason. So let V and W be subspaces of Rn. Then we say that V and W are orthogonal, and we denote it with the same perpendicular sign if every vector V and V is perpendicular or is orthogonal to every vector W and W. Okay, so we defined it for two vectors, and now we defined it for two subspaces. Okay, now, good question is, how do you show two subspaces are orthogonal? Okay, it's easy to show that two vectors, if I give you two vectors, it's easy to show that they're orthogonal, because you just have to do one computation. But if I give you two subspaces, then a subspace has infinitely many vectors in it, unless it's the zero subspace, right? A line through the origin has infinitely many vectors on it. A plane has even more infinitely many vectors on it. By definition, it's infinitely many conditions that you have to check. The way that you do this is you pick an arbitrary V and V and an arbitrary W and W, and show that V transpose W equals 0. What do I mean by arbitrary? By arbitrary, I mean in your argument, you're not allowed to pick a specific vector in V. You're only allowed to use the fact that V is in big V. The only thing you're allowed to use about the vector little v is that it's a member of big V. The only thing that you're allowed to use about vector little w is that it's a member of big W. Okay, so we should do some examples. Okay. And we should start where we're most comfortable, which is hopefully R2. Right, so in example, in R2, maybe the simplest example you can get, you take your first subspace to be the x-axis, call that V, your second subspace to be the y-axis, call that W, and hopefully you should believe that V is orthogonal to W. Right, so why is V orthogonal to W? Well, what I need to do is I need to pick an arbitrary vector from V and an arbitrary vector from W and show that they are orthogonal. So I can't pick 1, 0 and 0, 1. That would just show that those two vectors are orthogonal. But let's suppose that V is in V and W is in W. Okay, well, what is V? V is aka the span of 1, 0. W is aka the span of 0, 1. So every vector in V looks like some constant, comma, 0. An arbitrary vector in V, right? All I'm using is that it's in V. So since V is in the span of 1, 0, V is equal to C0 for some real number R. Again, I didn't pick a specific little v. Every vector in V has this property. All I'm using is that it's a member of the x-axis. Similarly, W equals 0D for some D and R. I don't know why I tried to do this all on one page. Okay, but then V transpose W is equal to c comma 0 times 0 comma d, which is clearly 0. And since in my argument I chose an arbitrary vector from V and an arbitrary vector from W, the point is that this argument works no matter which vector you pick. Therefore, every vector in V is perpendicular to every vector in W. Right? Since V and W were arbitrary, maybe I should say V and V and W were arbitrary. This shows that V is orthogonal to W as a subspace. Again, you can't choose 1, 0, and 0, 2. That just shows those two vectors are orthogonal, not that the subspaces are orthogonal. Okay, but that's the first example. But that's almost as easy as two vectors because they're both one-dimensional subspaces. So the next example to think about is a plane and a line. Right, so let's consider... Man, see, I should start the last example on its own page. You know what? I'm not wasting any paper. This is just OneNote pages. I can waste as much as I want. Let's take a look at, in R3, the xy plane. That'll be our V, and the z-axis. Right, so I'm inside of R3. This one's coming out of the page. And let's let V be the xy plane. That's horrible. Right, so this is V, and let's let W be the z-axis. Again, hopefully you find it very believable that these two subspaces should be orthogonal. Okay, and the argument is almost as straightforward as the last one. What is V here? V is the span of 1, 0, 0, comma 0, 1, 0. What is W? W is the span of 0, 0, 1. Now, how do I show that V and W are orthogonal? What I do is I take an arbitrary vector in V, an arbitrary vector in W, and I show that those two vectors are orthogonal. Since they were arbitrary, the argument works for any vector, any pair of vectors. So, well, what does it mean to be in the span of these two vectors? It means you're a linear combination of them, right? So let's let V be in V and W be in W. Since V is in V, therefore, what V is equal to is it's equal to some linear combination of these two vectors. So it looks like A, B, 0 for some A, B, and R. Every vector looks like this for some choice of A and B. Okay, and since W is in W, W is equal to C, it's a scalar multiple of this. It's equal to 0, 0, C for some C and R. So now I've written down what every vector looks like. Again, I haven't used any specific vector. I've chosen an arbitrary vector. But then V transpose W, the dot product, is equal to A, B, 0 times 0, 0, C, which is just A times 0 plus B times 0 plus 0 times C, which is 0. And again, now I've shown that every vector in V is orthogonal to every vector in W. So V is orthogonal to W as a subspace. Okay. But now, since we are mathematical people, you can generalize this to any Rn. So even if you can't draw the picture, so I guess I will encourage you to do this example yourself. It's really the same thing as the previous examples. If we let V be, the example in the notes gives you the xz plane in R4, and W to be the YW plane in R4. Whoops. Right, again, we can't really picture these because they live in four-dimensional space, but it's two-dimensional planes in four-dimensional space, and they will be orthogonal to each other because you can show it. So you should show that V is perpendicular to W, just as practice, okay? I've done this millions of times in my life. You haven't, so you should do it. It's exactly the same argument, though, as in the previous two examples. Okay, so this notion of dot product has given us a notion of length, namely the norm. It's also given us a notion of angles, in particular orthogonality, perpendicularity. Now I want to see that some subspaces that we know and love are actually orthogonal to one another. Okay, so a little bit of Math 308 review. So recall that if A is any matrix, so M by N, then we have the following natural subspaces associated to A. Okay, so the first one is called the column space. That's denoted COL of A. And there's more than one way to write it down. It's all the A times X's as X is in Rn. So every possible vector that you can get after you multiply by X. Since you're multiplying by X, since you're multiplying A by X, what you get is a vector in Rm. This is a subspace of Rm. Okay, and it's the same thing as the span of the columns of A. Okay, the fact that these two things are equal was discussed last week in lecture, as well as on your first homework. I think I saw, or before your first homework, I think I saw lots of Piazza posts about this. So if you're still confused, you should think about it. The second space you talk about in 308, although less than the column space, is called the row space of A. Okay, it's noted like this. Okay, and I'm going to give a definition that's very similar to that of the column space, which is you take y transpose times A as y varies over all vectors in Rm. And this is a subspace of Rn. And this thing is the span of the transposes of the rows of A. Okay, so let's take, for example, a 2 by 3 matrix. 1, 0, negative 1, 2, 3, 5. Let's call this A. The column space of A is just the span of 1, 2, 0, 3, negative 1, 5. That's, of course, a subspace of R2. And that's the same thing as the range of the linear transformation, which is the same thing as all possible outputs after you multiply by A. The row space of A here, I'm pretty sure that I want to write this as column vectors based on what's in the notes. This should be the span of 1, 0, negative 1, 2, 3, 5. This is subspace of R3. Okay, so we're taking the convention basically that every vector that we ever write is a column vector. If I want to treat it as a row vector, I have to take its transpose. Okay, so you can check that if you have a 2 by 3 matrix, you can multiply it on the right by vectors in R3, right? But you can multiply it on the left by vectors in R2. And you'll get out, well, you actually get out row vectors. So I'm misspeaking here. It's just the span of the rows of A based on what's written here. Sorry. Yeah, when you multiply this, you'll get row vectors. Okay. Okay, the point that I'm sort of bungling here is normally we think of Rn as consisting of column vectors, but it's really the same vector space as if you think of Rn as consisting of row vectors. In actual fact, they're what we would call dual vector spaces, but for finite dimensional vector spaces over R, over any field actually, the dual vector space is isomorphic. It's the same as the original vector space. So you can think of the row space as a subspace of R3, even though the vectors are row vectors, because changing the orientation of the columns doesn't change the vector space. It doesn't change how you add or scale multiply vectors. Okay, we also have the null space of A. That's denoted null of A in our notes. And that's all the vectors x in A, such that A times x equals 0. And this, of course, is a subspace of Rn, right? Because you can only multiply A by vectors in Rn. Okay. So notice that where these things are living, right? So the column space is a subspace of Rm, the row space is a subspace of Rn, and the null space is a subspace of Rn, which means that we have some hope of comparing the row space with the null space, right? The row space and the column space, in general, they live in different vector spaces, right? One of them lives in Rn, one of them lives in Rm. So I couldn't, for example, ask, are they orthogonal? Because I can't even take their dot product. But I can ask about the row space and the null space, because those do live in the same vector space. Even though, like, the row space consists of row vectors and the null space consists of column vectors, I can still sort of think of them as both living in Rn because they both have n entries. Okay, so it's a technical point. It's not really that important. Okay, but here's the results. I mean, this result is important. The worrying about row versus column vectors isn't really that important. So for any matrix A in Rm by n, the row space of A is perpendicular to the null space of A. This is the result. Okay, so now we're in an abstract situation where A could be any matrix, right? I'm not taking the span of 1, 0, 0 and the span of 0, 1, 0, whatever that is. I'm talking about any matrix, and I'm talking about these fundamental subspaces. Turns out they're always perpendicular. So our argument needs to be totally general. It needs to work for any matrix. So I need to take any vector in the row space of a matrix and any vector in its null space and show that they are orthogonal to one another. Okay, so how do we do this? So first, let's write A in terms of its rows. Right, so A is some matrix, but it certainly has some rows. It has m of them, because it's an m by n matrix, and these are row vectors, right? So I put the transpose here because normally when I write down a vector, I mean a column vector, and I'm saying take that and then transpose it. Technically, it's this way, I guess. Transpose it. Now I've written A in terms of its rows. Okay, so let X be in the null space of A. I need to show that X is perpendicular, is orthogonal to every vector in the row space of A. First, what I'm going to do is I'm going to show that it's orthogonal to every single row. Note that there's more vectors in the row space of A than just the rows of A. It's the span of the rows of A. But first, I'm going to show it's orthogonal to every row. Okay, so first, we show X is orthogonal to every row. In other words, if I take bi transpose times x, it's equal to 0 for all I. Why is that? Well, if you take a times x, x is the null space, so a times x is the 0 vector. Right, so 0, 0, 0 is equal to a times x, which is equal to this matrix times x. But how do you compute a times x? What you do is you take every row and you dot it with the vector. So this is b1 transpose times x, b2 transpose times x, bn transpose times x. Right, you just take b1, you just take this row and you multiply it by the vector. So what this shows is that for each I, bi transpose x equals 0. In other words, x is orthogonal to each of the rows. Okay, but I'm not done yet. I haven't shown that every vector in the null space is orthogonal to every vector in the row space. I've just shown that every vector in the null space is orthogonal to each row. Now I'm going to take an arbitrary vector in the row space. Okay, so now let's let it's not given a name in the notes. Let's let y be any vector in the row space of A. Well, what is the row space of A? The row space of A is the span of the rows. Which means that y is a linear combination of these things, right? So there exists scalars C1 up through Cm in R, just in R, such that y is equal to C1 B1 transpose up through Cm Bm transpose. That's what an arbitrary vector of the row space looks like. Right, so now I have an arbitrary vector in the null space, and I have an arbitrary vector in the row space. That's not where. Now let's take a look at their dot product. Okay, then y dotted with x. Really, okay, so y, as I've written it, is actually a row vector, so I don't need to take its transpose to multiply it by times x. This is a little bit sloppy in the notes, I think, but you get the idea. So let's just say y dotted with x here, so to avoid confusion, is just C1 B1 transpose plus Cm Bm transpose dotted with x. But we know that the dot product distributes over addition. So this is C1 B1 transpose dot x plus Cm Bm transpose dot x. But we showed previously that x is orthogonal to every row. So this is all just 0. In other words, I took an arbitrary vector in the row space and an arbitrary vector in the null space, and I found that their dot product was 0. That means that the row space is orthogonal to the null space. Since x was an arbitrary element of the null space and y was an arbitrary element of the row space, the null space of A is orthogonal to the row space of A. Okay, with a little bit of hand waving about whether they were rows or columns, but you get the point. If you take any vector in the row space, you take any vector in the null space, you take their dot product, you get 0. Okay, this I think is a good proof because it lets you see what's actually happening, right? I hope that you can all look at this proof and actually think about what's happening with the matrix multiplications and why this should be true. Okay, the notes also give a slicker proof, which is just using some notation, which is true, but I think it's a little bit less illuminating. Here's the slick proof. But honestly, understanding is more important than slickness, I think. The point is that the row space of A is defined to be all things that look like y transpose A, right? Such that y is an Rm. And the null space of A is defined to be all things that look like x, such that A times x equals 0, right? X in Rn, I guess. Right, so every element of the row space looks like y transpose A. So I should have chosen different letters probably. So if I take a v in here and a w in here, then what is v dot w, or v transpose w? I'm going to write v dot w. Well, v looks like y transpose A for some y, right? So really v is equal to y transpose A for some y, and w is equal to x. I mean, W has a property that A times W is equal to 0, right? So if I take V dot W rather, it's Y transpose A times W, which is Y transpose times AW, but W is in the null space, so this thing is just 0. So this whole thing is just 0. So you can get away with some sort of slick definitional proof, but I think this is actually less illustrative. So actually the slick proof here is worse, I think, especially since there's some confusion about row vectors and column vectors. Right? Really, the reason why I'm putting a dot here, right? Let me explain to you why I'm putting a dot here. Okay, so if you take these two vectors, if you take this to be V and this to be W, then they are orthogonal since V transpose W is equal to this times this, which actually is 0. Okay, but if you let this thing be V and this thing be W, you shouldn't take V transpose W. You should take V times W is equal to 0. So I put a dot here because really it's just V times W. It's not V transpose W because one of our vectors were row vectors. But again, I'm probably making a bigger deal of this than you need to care about. Okay, but let's go back to this more illustrative proof. And remember, I said, okay, well, there are infinitely many vectors in the row space of A. There's infinitely many vectors in the null space of A. But actually, it seemed like once we got to this point, we were basically almost done. Once we got that every row of A was perpendicular to X, it was very quickly followed that the entire row space was perpendicular, even though the row space has tons of stuff in it, right? All linear combinations of the rows. This is a general fact. If you want to understand whether or not two subspaces are orthogonal, you actually only need to check on a basis or a spanning set. But a basis is the smallest spanning set you can get. So here's the result that will be very useful in practice, because oftentimes I say the null space of this matrix, and you can just find a basis for it, right? And then you can do everything with the basis vectors. So suppose that V and W are subspaces of Rn. I wonder how much time I have left. I need to start setting timers. With bases, so let's call the basis of V BV consists of V1 up through Vk, and basis of BW of W, W1 up through WL, sorry, it doesn't necessarily have to be the same size, so this is respectively, of course. Then the whole subspace is perpendicular to the whole subspace if and only if Vi transpose Wj is equal to 0 for all I between 1 and k and j between 1 and l. Again, let me reiterate why this proposition is useful. To show that two subspaces are orthogonal, you show that every vector in this subspace is orthogonal to every vector in this subspace. There's infinitely many of those guys. But if you have a basis for each subspace, you have k vectors here that form a basis, l vectors here that form a basis, you only need to check k times l things. You dot each of the basis vectors with each of the basis vectors. If you get 0 every time, then the subspaces are orthogonal. So you don't need to pick, if you have a basis for your subspace, you don't need to pick an arbitrary vector. You can just check on each basis vector. Okay, so here's the proof. Okay, and this is an if and only if statement. In other words, it says if V is orthogonal to W, then all pairs of basis elements will be orthogonal. And if all the pairs of basis elements are orthogonal, then the subspaces are orthogonal. And the most classic way to prove an if and only if is to prove one direction, then prove the other direction. Okay, so let's do that. let's prove this direction. So suppose that V is orthogonal to W. Well, then that means that every vector in V is orthogonal to every vector in W. And the basis vectors of V are in V, and the basis vectors of W are in W, right? Then Vi is in V, and Wj is in W. Whoops. For all I and j. So Vi transpose Wj is equal to 0. Right? Of course, the subspaces being orthogonal is actually much stronger, it seems like, because it says infinitely many vectors are orthogonal. So it's actually the converse. That's where you have to do some work. So suppose that V is in V and W is in W. I'm assuming that each basis vector in V is orthogonal to each basis vector in W, and I wanted to show that the two subspaces are orthogonal. That means I need to choose an arbitrary vector in V and an arbitrary vector in W. Okay, but since V is in V, that means that you can write it as a linear combination of the basis elements. Right? Then since BV and BW are bases, what that means is that V is equal to C1V1 plus CKVK, and W is equal to D1W1 plus DLWL for some scalars, Ci and Dj. Now you just take their dot product. Then V transpose W is equal to this whole sum dotted with this whole sum. But now this is a matrix multiplication, right? It distributes over addition twice. Right? So really this will be, you take every term here and every term here, and you take the multiplication. These should really be transposes here. No, I mean, okay, transpose also distributes. Right? So really this is the same thing as C1 D1 V1 transpose W1 plus C1 D2 V1 transpose W2 plus every combination, right? So CK DL V, you can't see this, CK DL VK transpose WL. Right, this dot 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 here is every single possible combination, but each of these, I'm assuming, is equal to 0. So this whole thing is just equal to 0. Okay, so this is a nice, useful thing because you oftentimes do actually have bases of your subspaces in practice. And so you can check whether two subspaces are orthogonal by just checking if all their basis elements are orthogonal to all the other basis elements. Okay, so that's the row space and the null space. But you might be asking about, what about our poor column space? And is there a nice orthogonal subspace to the column space? And it turns out that there is, and it's actually not so hard to see why, because the column space you can think of as the row space of the transpose, right? So note that the column space of A is equal to the row space of A transpose, right? Because A transpose just takes all the columns of A and turns them into rows. So hence we have the following corollary, that the column space of A, which is equal to the row space of A transpose, is orthogonal to, well, the row space of a matrix is orthogonal to the matrix's null space. Right, so the column space of A is orthogonal to the null space of the transpose. Okay, so really, in 308, we learned about these three subspaces, the column space, the row space, and the null space. But Strang adds a fourth subspace that he calls the fundamental subspace, which he calls the left null space. I know it's kind of bad for me to put this at this point in the notes, but you can just write it and put a box and say another fundamental subspace. This is the null space of A transpose, and one way that you can write the null space of A transpose is it's the set of all vectors. Wow, I wrote this wrong actually. It's not x and a, this is x and Rn. It's been having a stroke when I wrote that. This is all the vectors y transpose in Rm such that y transpose a is equal to 0. That's why he calls it the left null space. It's like all the vectors that when you multiply on the left, you get 0. But of course, they have to be row vectors to multiply. Okay. We're almost done, but for some reason, in the notes, there's also this last result about matrix-matrix multiplication, which I assume means that it's important. At least for your homework. So I better say it in class so we are all on the same page. Here's the theorem. Let A be, it's an M by K matrix, and B be a K by N matrix. And suppose that A has rows A1 through AM transpose, and right, so these are rows, and B has columns B1 up through Bn. Right, so A here is M by K. So each of the rows of A is a vector in Rk, and B is K by N. So each of those vectors are in Rk. Okay, so there's two ways to think about multiplying A times B. Okay, so this is maybe the more usual way to think of A times B. This is a theorem from 308. Is you can think of multiplying two matrices as just multiplying the first matrix by every column of the second matrix. If you do a matrix multiplication, you'll understand. So this is just the same thing as the matrix whose columns are each of the individual matrix multiplications. A useful thing to see from this is that in the product AB, each row is A times something, which means that each column is A times something, which means that each of these columns is actually in the column space of A. So this is a linear combination of the columns of A. But another way you can think about this matrix multiplication is you can think of it as you take the rows of A and you multiply them each by the matrix B. And so you'll get A1 transpose times B down to AM transpose times B. And so each of these is a linear combination of the rows of A. Rows of B, sorry. Okay, so this is a useful fact. It's a fairly elementary fact. But let me just say one thing here, which is when you took Math 308, maybe you wondered why the column space seemed more important than the row space. I know when I teach it, I focus mostly on the column space. That's because the way that you do standard linear algebra, the way that you first learn it, is you learn everything with column vectors. And so when you multiply a matrix, you always multiply the matrix on the left and the column vector on the right. But you could do all of linear algebra with row vectors instead. And if you did all of linear algebra with row vectors instead of column vectors, you would write your row vectors on the right and your matrix on the left when you multiplied. And so what this is showing is that the rows and the columns here are sort of on equal footing if you switch sides. This is also why I like this definition of the row space and the column space. It really shows that the row space and the column space are the same thing, except one you're multiplying every possible row vector on the left, one you're multiplying by every possible row vector on the right. And the null space and the left null space are also kind of the same thing. So this shows there actually is a symmetry between the columns and the rows. The columns aren't more important than the rows. It's just that the way that we're used to doing linear algebra at first is with all column vectors, and so there's this artificiality that the column space is somehow more prevalent than the row space. Actually, there's a balance. There's balance in the force. All right. Anyway, this is our first lecture on orthogonality. I hope I went pretty deliberately through this stuff. Next lecture will again be on more stuff about orthogonality, and then we'll go into projections, and then we'll keep going from there. All right, see you next time.